Good morning, everyone. Can you please confirm if you can hear me? Just type yes in the chat box if you can hear me. Good morning, guys. I am reading your messages. Good morning, Ajay. Good morning, Lokesh. Awesome. Awesome. So, Bernie would be joining us very soon. So, till the time Bernie joins us, let's do the giveaway. So, are you all excited to learn today? Let me ask you the poll question. Good morning, Satya Prakash. Yes, that's awesome. 98% of you are all excited to learn. That's so awesome. So, without any further delay, let's do this. Just give me a confirmation if you can see my screen. Awesome. So, you guys can see my screen as well. So, what we are going to do is we are going to do a giveaway. So even yesterday we posted some of the quiz questions and a lot of you guys participated, which is amazing. So in total about 180 people participated in the quiz. So we would like to pick one person out of this 180 people and then give a surprise gift. And the way we are going to do that is using random number generator. This will ensure that we are giving fair chance to everyone. So just to check if it's working properly, I'm going to randomly put number 1000 and I'm going to click generate. So we can see it's generating some random number. So I believe it's working perfectly fine. So serial 180. So I'm going to put minimum 1 and I'm going to put maximum 180. So the moment I click on generate, then whatever is the number that's going to show up here in place of the 615, that corresponding person is the winner. So without any further delay, let's do this. 3, 2, 1, go. Number 150. So that is Komireddy Nagarjuna. So, Mr. Komireddy Nagarjuna, congratulations. You are a lucky winner today. Our team will get in touch with you with the process on how you can get it. So, congratulations, congratulations, Nagarjuna Komireddy. And now let's get back. Awesome. Are you in the session, Nagarjuna?
Yeah, congratulations, Nagarjuna. Great job. And you'll receive a call from our side to give you the award. Okay, having said this, Enoch, have you also shown the YouTube link? Because a few of them are still asking me in private on how do I get access to the videos? Maybe they joined in late, maybe they are unable to view. A few of them are saying that we are unable to view the URL that you post on the chat because a lot of chat messages come in. And when we connect from mobile device, when you put it in the sticky note, it goes unnoticed. And we are also posting on the WhatsApp. So I'm sensing this person is not there on the WhatsApp. So maybe you can just quickly show the YouTube and then, yeah.
All right, let me do that. So let me first open our YouTube channel. So all you need to do is just go to YouTube, type in 360DigiTMG, and it will bring you to a page like this. And while you're here, just let me open our playlist, specific playlist.
Playlist would be different. So yeah.
Yes. So what you need to do is you need to go to our playlist, and here right now you can see it's from day 1 till day 10, and today is day 11. So day 11 would be added as, so we are also going YouTube live, which means day 11 would be parallelly running here.
I think day 9 is getting repeated twice. We might have to remove that.
All right, yeah, sure, but we'll take care of it. So this is the link, guys. I'm gonna post it in the chat just for the person who is unable to get it. And yes, and Rajkumar, I'm just looking at your message. I'm gonna dig into that. And over to you, Bernie.
Yep. Thank you. Sure. Thank you so much. And welcome once again to today's session. This is a session which has been launched in collaboration with you know Andhra Pradesh State Skill Development Corporation and 360DigiTMG, Digital Transformation Management and Governance. And yep, welcome to the training. Today we are going to discuss about a different concept, a different neural network algorithm altogether. But even before we proceed further, I would certainly like to walk you guys through all the concepts that we have discussed until now. I want to quickly show you the mind map that we have, and then suppose that it will start making sense. So I think I wasn't sharing my screen, my bad. Okay. So once again, welcome to Faculty Development Program on AI and Deep Learning. Before we proceed further, I am assuming that a lot of you all want to have a quick recap of the complete session that we have done until now. And to do that, you have to just allow me a minute while I try to pick the mind map, which is called as free mind, not the mind map which is there on our website, but the other mind map. And I want to uh, do a quick comprehensive recap of all the concepts that we have discussed until now. And I'm sure you're going to actually love it. So just give me a bit while I pick up the most recent of the mind maps and while I launch that. I'm launching, so post launching, yep, I am going to share my screen now, and let's delve deep into the world of AI. So this is what I mean by mind map, and let us do a comprehensive recap. So we started off by discussing about project management methodology, CRISP DM. Okay, and then we started off by discussing about machine learning primer, which is available in this. As part of machine learning primer, we discussed about how do you understand the business problem, how do you record the, how do you create project charter, how do you collect the data, what are the various data cleansing preparation which happens, and then supervised learning techniques, within which we started off by discussing about, one second, I'll just minimize the entire thing. And also I will just zoom out a bit. Okay, we started discussing about perceptron algorithm, and perceptron algorithm is something which is used to handle linear boundaries, linearly separable boundaries. And we also understand here within this deep learning primer that the perceptron algorithm has a single output layer, single output neuron rather, and it has no hidden layers. You will not have any hidden layers. You'll have a single output neuron. And when you update the weights, we use backpropagation algorithm. And the objective is to reduce the weights. How do you update the weights? New weights is equal to old weights plus eta, which is called as learning rate. You multiply eta with true value. True value means it's the actual value minus predicted value, and you multiply it with the input vector. This is a formula to update your weights. But since this handles only linearly separable boundaries, we also have multi-layer perceptron or artificial neural network, which handles non-linearly separable boundaries. Okay, also to handle the non-linear pattern, we can use different kinds of integration functions. Okay, so I'll put it here. Using different integration functions, we can have a model handle non-linear boundaries. So what could those be? A few of those things which we have discussed includes quadratic function and spherical function. Okay, we discussed about these things. Then we discussed about a lot of activation functions which exist, which would come here in deep learning primer. Okay, you have, okay, it's given here. I didn't see that. Okay, all right. Anyways, so this I would like to delete. I would like to delete even this component of it. Then we'll discuss about this, right? So we have artificial neuron, which has integration function, which can be quadratic and spherical also, alongside simple summation. It could be summation, or it could be quadratic, or it could be spherical. Then we also have activation component, and this activation component is something which brings in the non-linearity. If you want to capture non-linear relationship patterns in your data, then we need to have activation functions. However, if we use an activation function which is linear, identity function, then this will not handle non-linear patterns. Okay, this is not going to handle non-linear patterns. I don't know where I got that sound from. Okay, anyways. So here, so we have these linear functions, right? Linear function is one thing, and then we have step function. Within step function, you have stair step, unit step, heaviside step, sine function, ramp function. We have piecewise linear functions, which includes ReLU, rectified linear unit, leaky ReLU, noisy, parameterized, shifted. Then you also have a lot of smooth functions, which includes ELU, sigmoid, logistic, tanh, swish. Then you have max out, then you have soft max. Soft max is something that we use when when you want to take output values of all neurons of output layer and normalize them so that summation of all probabilities is equivalent to 1. Okay, and sigmoid or tanh is used when your output variable is discrete in 2 categories. And we use linear function when output variable is continuous. That is when you use that. And when your output variable is when your output variable is discrete, and if you have 2 categories, we use sigmoid or tanh. Okay, so I would rather put it here. Then I would bring in sigmoid and tanh here, then probably the smoothened versions. Okay. Okay, let me also mention here that then output layer usually has these activation functions. That means intermediary functions, intermediary layers can have any activation functions, ReLU, etc., tanh, you can use anything. But I'm speaking specifically about the output variable here. Okay. Then output layer has linear activation function or no activation function. And when we say no activation function, that means it's by default going to be linear. And when you have your output variable, which is discrete, and if it has more than 2 categories, then we use this activation function in output layer. Okay, these are the bunch of activation functions which we have discussed. Then we also discussed that. We also discussed about a lot of optimization functions. So I think I should bring in activation functions, optimization functions here. Just give me a bit while I go here to the optimization algorithms, and I'm gonna take that and put it here. Again, I would take the optimization and put it here. Now I'll zoom it and then explain once again. So we discussed about 3 of the optimization functions, which is batch gradient descent, stochastic gradient descent, and mini batch stochastic gradient descent. But mini-batch stochastic gradient descent has certain issues. So we can use momentum, Nesterov momentum, or ADA grad, ADA delta, RMS prop, or Adam to handle these issues. But then it actually makes sense for all of these to be represented separately. All right. Then we also discussed about the libraries, deep learning libraries. What are the deep learning libraries which exist? One is TensorFlow from Google. This is from Google. It is open source now. We have Keras from a person by name Francois Cholet. And we have PyTorch. Group of people have launched this, PyTorch. Then we have MX uh, Net. This is from, if I'm not mistaken, Amazon. And then you have Cafe, you have Piano, you have CNTK from Microsoft. Different companies are coming up with different ways, different versions of libraries. But world's number one today is TensorFlow, which is called as low-level programming language. But in TensorFlow, the latest version 2.0, 2.x, 2. Whatever be 2.2.0 or whatever be the version that we exist, officially says that or officially recommends Keras. It officially recommends Keras. Just give me a minute. Sorry, my so a few of our people do not know that I'm in training, so they keep calling. Sorry about that. Okay. So TensorFlow 2.0 officially recommends Keras to be used. Keras is a high-level programming language. And this is awesome. PyTorch is also a low-level programming language, which is fast picking up the attention of the world. Okay, the minute differences between these is out of scope for this FDP program, but then, yep, it makes sense for you all to understand about the minute differences between, the various things. Okay, and then we started off by discussing about, I'll put this here, deep learning primer. Okay, and then comes computer vision, so I'll put it down there somewhere. So we then switched our gears to discuss about mathematical foundations. Within mathematical foundations, while we have done data optimization, we have discussed about rate of change, which is also called as derivative or scope, or sorry, slope or gradient. All these are the various names given to rate of change. Okay, I can also make it better for you guys, is also called as derivative or gradient or slope, all mean the same. And then you have rules of derivatives. We looked at power rule, constant rule, sum rule, difference rule, product rule. And then what are the other rules that you remember that we have discussed about? A lot of rules is what we discussed. Power rule, constant multiple rule, sum rule, difference rule. Then we discussed about this product rule. Then we discussed about um, quotient rule, like division basically, right? And then there is also another important rule called as chain rule. Okay, and then we have looked at the procedure to find, you know, minima or maxima. Then we have linear algebra also, then we have probability also. That's fine, but these are all your mathematical foundations. That was the next thing that we have looked at. So machine learning primer, deep learning primer, mathematical foundation is what we have discussed. Okay, and inferential statistics, probability distributions, the various data types can be actually clubbed with. I don't know why it's not moving once again. Yeah. So this data types can be part of data collection here. And only after you understand about the various data types, you proceed further with primary and secondary data sources. All right. After this, we have also looked at a lot of practical challenges which one will face. Okay, once again, I need to do this, I think. Okay. We discussed about a lot of practical challenges with respect to deep learning and a lot of practical issues and how do we address those. So there are a lot of challenges here. So I'll put it somewhere here that we have a lot of deep learning challenges and practical issues. As part of deep learning challenges and practical issues, the one thing is you have umpteen number of options, various options to choose. For deciding the best neural network setting. For example, you need to choose the number of hidden layers. You need to choose number of neurons in each hidden layer. This is also another thing that we need to do, look at. And then you need to decide on what activation functions should I use. To a great extent, what activation functions you need to use in the output layer is clear. But what do you use in the intermediary layers is something which is not clear. Okay, it is not clear. Basically, we need to figure out on what is it that is going to make a good impact in terms of giving you better accuracy. And the next thing is you need to decide upon what should be your error function or loss function, loss function. As part of our machine learning primer, these things would be explained in detail, right? So if I were to go here, we have machine learning primer, which is used here, wherein you split the data into training, validation, and test, and you do this comparison. And you have model accuracy measures. And you also have error functions, right? So model accuracy measures, I would call these as basically error functions. These are primarily used to evaluate the model performance. And to evaluate your model performance, you need to look at whether your output variable is continuous. If it is continuous, you have all of these: mean, error, absolute deviation, so on and so forth. If your output variable is discrete in two or more than two categories, you proceed further with confusion matrix, cross table, or contingency table. The bunch of these which exist. Okay. Then, yeah, majorly these two. And then we also have cost functions. Cost function versus loss function. First, let us understand what is the difference between these two. Okay, you can also use kappa statistic, and there are various other things such as archaic median, etc. And Gini is more or less a cost function. So first, what is a cost function? Cost function, okay, is okay. Here it is already given. Cost function is for if you or aggregate of all the loss functions, and this is for entire dataset together. So you calculate basically. I'll first take loss function here, then I'll put the cost function. I shall delete this part. Okay, and then this I think I would take here. Then residual and error, fitted values, predicted values, I think should go here. Okay, loss and error. So here, loss function or loss functions is for, it is the loss calculated for each row. Row is called as observation. Observation is called as a sample. It is also called as example. It's called as instance. It is called as cases. All these terminologies mean the same. And when you aggregate all of the loss functions, you get a cost function. When your output variable is continuous, okay, the loss function or the cost function would be the same. It will be the same. However, when your output variable is discrete, in two categories, we use cross entropy. Okay, you use cross entropy, and there you can either use categorical cross entropy or binary cross entropy, but here it is binary. And if your output variable is discrete, and if you have more than two categories, then you proceed further with again cross entropy only. Uh, Again, you proceed further with cross entropy, but the only difference is that you proceed further with categorical cross entropy. Here it is binary, here it is categorical. And KL divergence is also one of the measures of cross entropy. Put it here. You can use it when your output variable is, um, you know, two or, more than two. So I can just put it here in that way. We can also copy it for this. And we also have Gini index. It is also like your cross entropy basically. You can also use that primarily to measure. So I'll put it here. And all right. So if you understand these aspects, it will be a very, very smooth sail for you. Okay, you'll understand a lot of aspects and it'll be easy sail. Then back to our various options that we have. So you need to decide upon the loss function, cost function, etc. You need to decide upon what gradient descent method will be used. And within that, again, you need to decide the size of mini batch, values of learning rate. Learning rate ranges from 0 to 1. What should be the learning rate value that you need to choose, which is also called as eta value? Okay, all these things are important. And in each of the gradient descent algorithm, you have different parameters that you have to choose or decide. Having said this, we have that L1, L2 regularization technique, of course. And we also have something called as vanishing gradient problem or exploding gradient problem, which we'll discuss in further detail. Yeah. And here, what happens is weights might be randomly initialized with greater than 1. If the values with values greater than 1, then what happens is you run into an issue which is called as exploding gradient. Because if you have values, all the weights which are greater than 1, and if you keep multiplying those numbers, for instance, say you have all these neurons, and if the weights that you have are greater than 1, then you multiply this input with this weight which is greater than 1. So you ultimately will get a value here which is greater than 1. This greater than 1 value, again it gets multiplied by another weight. If this also is greater than 1, it will keep exploding. It will become larger and larger. At the same time, we also have something called as vanishing gradient. What do you mean by vanishing gradient? Vanishing gradient means if you have the same neurons like this, and if the weights which are initialized here are less than 1, for example, if you take 0.8 and say this is 0.7, if you multiply these two values, you get 0.56, which is much less than these two values. So slowly and steadily it will get to a value which is closer to 0. That means if you have a gradient like this, if your weights get initialized here, it will move on and then it quickly reaches 0. Means it will stop learning, but your deepest valley is here. You will never reach the minimum error. These kind of challenges arise. This is vanishing gradient problem. So here, if the weights initialized are less than 1, then quickly the end result, quickly the weights, not weights, the, outputs of neurons in subsequent layers vanish to zero. Okay, how do you address this is a again big problem, right? So overcome this challenge by batch normalization. Okay, we discussed I think about batch norm. So yep, there's one thing. And then even when you consider the learning rate, this learning rate eta value, it ranges from 0 to 1. Right? And once again within this, there are new things that we need to understand. You will have fixed learning rate, which has again a challenge, which we didn't discuss, but it's called as bouncing around the bowl problem. To counter this, people have come up with shrinking learning rate. Look at deep learning. I mean, now I'm sure you all will agree that deep learning and AI experts should be paid more salary, right? I'm pretty sure you all are aware. You all will agree with me on that. And when it comes to shrinking learning rate, you have exponential shrinking, you have bold driver technique, you have a step technique, okay, and then there are many other techniques, delayed exponential technique. There are a lot of techniques which exist. Okay, so again, you need to decide number of iterations, number of iterations, number of epochs. All these are a few things that you need to decide. So it becomes extensively, complicated. And then there is a very big problem called as overfitting. Overfitting, right? Overfitting can be addressed using a lot of regularization techniques. And when it comes to regularization techniques, you have something called as early stopping. Within early stopping, again, you have something called as error change criterion, and you also have something called as weight change criterion. Then, not just this, you also have something called as dropout. You have something called as drop connected. Then we have something called as noise that you add. You can add data noise. You can add label noise. Then you can add gradient noise. There are a lot of noises. Okay? Not just that, again, there are a lot of other techniques which exist, such as we have something called as data transformation. Batch normalization would come in here, which we put there, but let me also mention here. Then you have a concept called as shuffling the inputs. And we have something called as curriculum learning. Then when you deal with images, today we are going to get into this. We will get into something called as data augmentation. Okay. We also need to, alongside this, look into something called as co-way, create shift issues, practical issues. We need to look at correlation between inputs. And if you have correlation between inputs, it is called as collinearity problem. How do we address this? Once again, is a challenge that we need to look at. And one people keep asking this question, batch normalization. Add batch normalization layer between fully connected network, which is called as dense network, and activation functions or activation layer. So in between we add it, usually batch norm. And there are a lot of other techniques. Throughout as we talk, we will be discussing about that. And then one more thing is weight initialization. Okay, here I would put that here, wherein you again need to decide upon what weight initialization technique would I use. Would I resort to random weight initialization technique which exists, or would we go with Savier's technique, which is also called as Glorot's, or would you go with He's initialization? Okay, is a call that we need to take. Glorot, Xavier. So all these are the various techniques which exist. Let me put it as this because it's the name of the person. Okay. A few people do a normal initialization. A few people do uniform distribution initialization. There are many, many ways. So normal distribution, uniform distribution, but none of these have shown to give exceptionally superior performance. It gives some performance, but not exceptionally superior performance. Okay, so these are all your practical issues. Then we didn't stop there. We proceeded further with computer vision, which is a different study in its own. And then we discussed about what are the various things which your computer vision addresses. So I'll put it as image processing and video analytics goal. Tomorrow you should not get confused between convolution neural network applications versus computer vision applications. So you have verification, you have detection, pose estimation problems, activity, classification problems. We have object categorization problems. We have scene categorization problems. You have attribute categorization problems. If you want to apply a simple facial recognition algorithm, or if you want to solve that kind of a problem, we can still solve it. Okay, and then after this, we started discussing about the various challenges that we have. The challenges that we have is to handle intra-class variation. And there's something called as viewpoint variation that we have discussed. All these things we discuss, my dear friends. Illumination challenges. Then sometimes you might have background clutter. Then you might have occlusion related issues. Then you can have pose deformation issues. Then you have large number of categories to handle. These are the various challenges that we have. Then we took a basic image. We know that image features, I'll put it as image features to be extracted. The most raw feature that you can extract is from an image is nothing but pixel intensity values. And if you have a number 0, it is black. If you have a number 255, it is white. Even if it is a color image, we can do this. And we've also discussed that image can be represented as a function. The moment you represent image as a function, you can do a lot of image transformations. What did we discuss? We discussed about transformation wherein we increase the brightness of the image, flip the image along an axis, along x-axis or y-axis, right? And then we looked at 3 operations, which includes local, point, and global. And then we moved on to discuss about a few more point operations, such as we can do reversing the contrast. Okay. You can do histogram equalization to stretch the contrast in an image. So all these are the point operations. In fact, these two are also point operations, increasing the brightness and all that. Of course, there are various other ways of handling it. And we can also use point operation. Oops, sorry. Yeah, we can use this point operation to one of the users is to reduce the noise. Okay, and then you can extend this to 1 dimension, 2 dimension, right? And then we venture into something called as, yeah, that's noise reduction bit that we have looked at. Let me also put it here. Then we started looking at filters, kernels, or masks. Filter or kernel or a mask mean the same. So we have a filter, we have a kernel, and mask. All three mean the same. And let me edit this. Okay. So we have a linear function, which is also called as a mean function or a box function. Then we have looked at an operation which is called as cross correlation. Like you have addition, subtraction, deletion, and all that. We have cross correlation and convolution. Convolution doesn't have any drawbacks, shortcomings, but cross correlation has certain limitations. Hence, people are using convolution, and hence we call it as convolution neural network. And this mean filter, etc., is also called as smoothing filters. Right? So you have lean filter or box filter. Here, amount of blur depends on filter size or kernel size or mask size. Okay. But then the disadvantage here is that boxy, okay, box-like appearance in the filtered image would appear. Hence, what we do is we try to fix that using Gaussian. Okay. The drawback of box filter is addressed here. Here, the amount of blur depends on the variance value. Okay, we looked at the sigma value and all that. What is another property of Gaussian? Central pixel is given highest weightage. Okay, and then neighboring pixels are given next or high importance, and diagonally and diagonal neighbors are given least weightage. So all these are the various things that we discussed. It serves as a very good recap for you all to remember on what we have discussed. Not just the variance value, but it also depends on the filter size. There is a condition, okay, or properties of smoothing filters. Not all the filters, okay. Smoothing filters have certain properties. What are those properties? All values should be positive. Sum of all values should be equivalent to 1, right? So these are a few properties that you need to remember. And then we have started applying these filters, and then we have seen what were the implications of that. And then we discussed about boundary effects. Boundary pixels are gone. You address it using padding. We have zero, padding, wrapping, clamping, mirroring. All these are the various techniques. Then combination of certain filters will give you sharpening filter. So what we have done is we have applied a brightening filter and we subtracted it from the smoothing filter. And when we have subtracted these two, we got sharpening filter. The point here is combination of filters give rise to new filters. It will do different other operations. Then we have discussed about template matching. Okay, so take a template and cross correlate the filter. This filter template is like a filter on input image. Then wherever we have a bright spot in the output image, there will be the exact match. Okay, you'll have an exact match. Okay, so the grammar part, we need to look into it. Then we moved on to discuss about edge detection. Edge detection filters. From there, we started dealing with edge detection filters, wherein we discussed that edges are formed. Let me first put that. Edges are formed at a place where we have maximum change in intensity values, okay, between pixels. And how are edges formed? This also we discussed. Origins of edges. We discussed that whenever there is surface color or appearance discontinuity, or wherever you have depth discontinuity, wherever we have illumination discontinuity, and wherever you have surface normal discontinuity, edges are formed. Okay, this is also one thing that we discussed. Then we applied Sobel edge detector. We discussed about Sobel along x-axis, and we discussed that this will detect vertical edges. Then we have also discussed about Sobel along y-axis, and here it will detect horizontal edges. Okay, we didn't stop there. We discussed about Prevet, which will also find the vertical or horizontal edges. Finds vertical and or rather horizontal edges. Then we have also discussed about Roberts. Robert is going to help you detect edges along diagonals. And we have also looked at a formula for the angle, orientation angle. Orientation angle of edge is given as tan inverse. Let me put tan inverse of partial derivative along y divided by partial derivative along x. Okay, so this is something which will help you find the orientation of the angle. Then we discussed about how to reduce the noise. Reduce the noise in detecting the edges. How did we do this? We actually took the input image steps. So take input image, okay, then take Gaussian filter. This happens to be step 2. And this happens to be step 1. Then what you do is convolve. Convolve Gaussian filter on input image. Okay, and then the end result will be a smoothened image, and then find the derivative of the result of step 3. Then we looked at an improvised version. In improvised version of these are very important from practical applications. Yeah. Say you want to detect an object while you have a driverless vehicle in place. How would you do that? Yeah, those kind of scenarios, it comes in extremely handy. So what you do is step 1, take the input image. Step 2, take the derivative of Gaussian filter. Step 3, um, convolve the result of step 2 on input image. That's it. This will actually help you reduce the noise. Then we discussed about Laplacian filter, which is majorly used to identify the blobs. This is nothing but second derivative of Gaussian filter. Then we also discussed about reducing noise using nonlinear filter. So let me put it here. So we have discussed about non-linear filters, non-linear filter to reduce the noise, and we have actually used median filter to reduce the noise. Okay, and we also have bilateral filter, which is used to reduce the noise. And then we switched into canny edge detector. Okay, so where do I put this Laplacian filter? Okay, let me put it here. Then I'll put blob. Then I'll put this. Okay, here. We've done all these things. I mean, it's a very, very comprehensive recap that I'm doing so that when we move on further, you do not have any trouble in understanding. So we have this canny edge detector. I think it would take some more time to do this recap, maybe another 10-15 minutes, but it's already 11:40 now. So I believe we need to take a break. Let us take a break, come back, complete this part, and then we will get started with convolution neural network. So it's approximately 11:40 now. Let's be back by 11:50. Oops. Let me Yep, hello. Let's get started. Yeah, sure. We will put it on our website. Not a problem at all. Okay, this mind map will come in very handy for you. We will put on our website and share the URL with you guys. This is how it works. You just double click on that and it will give you the results. So we have this canny edge detector. Okay, and how does it work? Steps. Step number one is that you apply Sobel along x-axis and Sobel along y-axis. Then combine the results by taking a gradient. Combine the results of Sobel along x and y axis. Okay, once you do this, the third step is you do non-maximum suppression to ensure that okay, we get a single edge. And then you move to the fourth step. And the fourth step is you apply hysteresis thresholding. In this hysteresis thresholding, we apply a minimum value and we apply a maximum value. Okay, this is what we discuss. Then what did we discuss? Sharpening filter, edge, all these things are done. Then we discussed about image sampling techniques, right? Wherein we discussed about subsampling, means reducing the size, in which we discussed about the challenges with respect to uh, not choosing a right sample. So we discussed about image aliasing effect, wherein we discussed about Nyquist rate. Okay, and then we discussed about Shannon's sampling theorem, which says that the sampling frequency should be greater than or equal to 2 times of maximum frequency. 2 times of maximum frequency. Okay, and then we have also discussed about this, wagon wheel effect, etc. Then we discussed about how do we subsample with Gaussian filter. So what should you do? Apply Gaussian filter on the image and then subsample, and then keep subsampling. Okay, we have also in the interim looked at Gaussian pyramid or image pyramid, which is a result of Gaussian pre-filtering. Okay, it's a result of Gaussian pre-filtering. Then we have also discussed about upsampling, which is called as image interpolation, meaning you want to increase the size of the image. How do you increase the size of the image is something that we have discussed, in which we have a lot of techniques such as nearest neighbor technique, then linear interpolation, then we have bilinear interpolation, we have then bicubic interpolation. So these are bunch of things that we have discussed. And we didn't stop there. We moved on with the practicals. Right? When we moved on with the practicals, we have looked at various other things such as, I'll put it here, practical world using OpenCV. OpenCV stands for computer vision, open computer vision. And what did we do on this? We have looked at how to read and how to view and how to save the images. This is one major concept that we have looked at. Then we have looked at converting images from one color space to another. Then uh, what we have looked at is splitting the various color channels and combining the color channels. This is also another thing that we have looked at. And then we have looked at various transformations such as image translation. Then we have looked at rotation. Then we looked at scaling, different scales. Okay, then we looked at affine and projective transformations. Then we applied all of these, various filters. One very important thing that we looked at is detecting human face and human body parts. Okay, we have done this using something called as R. Amazing thing that we have done, right? And then we have finally looked into seam carving. Okay, once we were done with seam carving, seam carving is all about removing or adding uninteresting points to downsample or upsample the image. Okay, this is what we have done, and there are a lot of computer vision applications that we have built, such as object detection, image scene segmentation, and a bunch of those. But we'll be dealing more. We'll be doing a lot of stuff also. All right. So this is the kind of ground that we have covered, and I'm not sure on how you're feeling, but then if you just look back on the kind of depth that we have covered, it is amazing, right? So I request you all to have access to this. I will upload this immediately today. I will have it uploaded today itself to the system, and then you'll actually enjoy it. Okay, so I'll delete this from here because we put that elsewhere. Okay, works back on back propagation to update weights. I'll just delete this. All right. So now we are venturing into something very, very important, which is called as convolution neural network, which is all about dealing with videos and dealing with images. Okay, so before we get started with convolution neural network, as usual, we will go through the theoretical aspects. So I need to open CNN part first. There we go. Welcome to the world of convolution neural networks. This is by far the best neural network algorithm to deal with images and videos. A lot of applications today are working on this, and a lot of competitions which you're seeing nowadays is based on this. How did this become famous in the first place? And why did this become famous? There was this competition called as ImageNet competition, wherein people have come up with 14 million images. 14 million images, and people have hand annotated. By looking at the image, they have given a name to all the various images. And when they looked at the different categories of images they had, there were 22,000 categories. And these folks thought, all right, we have spent, you know, years of effort in manually giving a label to an image. So if there is an image, for example, someone has to look at this image and say that, okay, there are birds in this image. Someone there, if there is another image, someone has to manually look at this and give a name that, okay, this is a fish or a blue whale, so on and so forth. Then they thought that the amount of images that we deal with is just going to get exploded over a period of time. Okay, it's going to get simply exploded. So what do we do? Since the number of images would get exploded, people thought that they will use a competition. They will resort to competition, and they resorted to a competition which was called as image large scale. Um, let me open that. Let me open that here and then show you that. So ImageNet competition, this one. So it was called as ImageNet Large Scale Visual Recognition Challenge. Okay, they started this way back in 2010, and I'll speak more about this. Then they thought, we want people to solve this problem wherein if an image is provided as an input, okay, how do we instantly recognize on what this image is? And they have given 1.4 million images and 1,000 categories. So in your output, it was a 1,000 class classification problem. If there is an image given, there were 1,000 categories which were given that, hey, is this a bird? Is this a fish? Is this a drum? Is this a panda? Is this a car? In that way, there were 1,000 categories, and your algorithm is supposed to look at this image and automatically give probability values, saying that no, there is only 0.001% probability that it's a bird. There is 0.03% probability that that's a fish. Oh, there is 90% probability that this is a drum, right? In that way. And whichever class has the highest probability, that would be chosen as a class label. Okay. And what has happened is in 2010, there was some classification error of around 3%. In 2011, people tried for entire 1 year, but then they could reduce error rate by only so much. Very small improvement. For after one whole year. Then in 2012, the improvement was significant. Then the entire world started looking at this, saying that, okay, How come there is such a large improvement? And when they started digging deep into that, they found that people used something called as neural network. Okay, they used something called as neural network. And the first time world noticed that was in 2012. Back until then, we had neural network, but it wasn't so famous. And the team from University of Toronto, Canada, Alex Krzyzewski, has actually taken this forward. And after that, every year, the competitions which were won in this ImageNet, all those algorithms used neural network architecture, which was nothing but convolution neural network architecture. There are a lot of challenges, which were addressed eventually, such as if I give this image as an input and if I ask people to detect on how many people are there, and you're 1, 2, 3, 4, 5, but then your computer would also look at the mirror and it would classify or it would count even this person. It would look at the mirror and count this person as another person. So there are a lot of such challenges, but all these are addressed now. Object detection, object segmentation, right? Detecting what is there. And then self-driving vehicles need that for detecting the objects. Not just detecting and but also predicting on what is the probability that this person would come in front of this vehicle or this person would come in front. Pose estimation, is a person sitting or opening a door or walking or running, so on and so forth. Different signages, different language alphabets. For all of these things, people started heavily using convolution neural network. Today, as we stand, when it comes to facial recognition systems, it's convolution neural networks. Detecting the whale, overlaying a map on top of the already existing map, image captioning. Okay, all these are examples of convolution networks. You just look at that image and classify on what's happening. But there is a disadvantage, a very big disadvantage. If you use the regular multi-layered perceptron or artificial neural network in handling images. For example, there is a dataset called as Cipher 10 dataset. I can show you that. There is also Cipher 100 dataset. Okay. So this Cipher 10 and Cipher 100 are datasets which contain 60,000 32 by 32 size color images, and it has 10 classes: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of these 60,000, 50,000 belong to training and another 10,000 belong to test. 100 means you'll have a 100 class problem. Here you have 10 class, there it's 100 class. If I take such a small image, this is considered to be very small image. In the present world that we live in, easily we are getting megapixel cameras. And if you take an image, they say, hey, images will be of 10 megapixel. That's a quality. Megapixel is 10 raised to the power 6. If it's 10 megapixel, 10 raised to the power 7, that'll be so many zeros. It's going to be huge, huge, right? It is simply put 1 crore, right? 1 crore images is what we are speaking about here. Anyways, pixels is what we are speaking about along one dimension. If it's 10 megapixel camera, do you know what? you'll have 10 raised to the power 7 columns and 10 raised to the power 7 rows. It'll be huge data set. Let us understand here. In Cypher dataset, if the images are only of size 32 by 32, okay, even before that, I think it makes sense for me to ask a question because I'm not sure on whether you guys are aware on calculating the number of weights when it comes to our artificial neural network. Okay, so what I shall do is I'm going to ask you a specific question. Okay, let's see who will get it right. So question is as follows. If I give you a multi-layered perceptron with 10 features, 10 inputs. Okay, so in your dataset, underlying dataset, you'll have 1, 2, 3, 4. In that way, you'll have 10 inputs. All right, and say you have a hidden layer, only one hidden layer with 20 neurons, and you have an output layer with a single neuron. For this, and if it is a multi-layered perceptron dense network, then how many weights will your model learn? How many weights or parameters will your model learn? Yep, please answer this. So I'm saying that in the input layer, you'll have 10 features, and on your hidden layer, you'll have 20 features, and you'll have an output with a single neuron. And I'm speaking about a dense network, meaning all the neurons, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the neurons will be connected to all these 20 neurons here. 1, 2, 3, 4, in that way. So all the neurons will be connected to all the other neurons in the forward layer. So how many weights will your model learn here, and how many weights will your model learn here? Because if you have 20, and if all 20 are connected to this, then how many weights would be there? Yep, please answer. Let me see how many of y'all will get it right. You can take quick 2 minutes to address this. 2 minutes. But then I do not want you guys to go wrong here. Please focus. Okay, take quick 2 minutes to address this. Let us see how many of y'all will get it actually right. Yep. Okay, I'm going to give you 1 more minute to answer this. Let me see what happens. All right. So I think I need to answer now. So if you have 10 neurons in the input layer, and if you have 20 here, each neuron will be connected to 20 neurons. Each neuron will have 20 neurons because it's a dense network or a fully connected network, meaning every neuron will be connected to every other neuron. If you have 10, if you take each neuron will be connected to 20. If you have 10 neurons, they'll be connected to all 20. So you'll have 10 multiplied by 20. But then remember, there will also be an additional neuron, which will be always having a number 1. And it will also be connected to all these neurons. And that will be called as bias, the weights. So you'll have 10 plus 1 bias. And all those neurons will be connected to 20 neurons each. Plus, this part is done. Now, from 20 to 1, each of these 20 will be connected to one neuron. So you'll have 20 connections. But then you'll also have a bias, which will always have a 1. So plus 1. So these are the number of weights that your model will learn. Okay, so 11 into 22 will be 220, right? Plus 21, which will be 241 neurons. Okay, since you have 241 weights or parameters that your model is going to learn, the number of weights is fine. But then if you have images, a decent image will be at least 1 megapixel. 1 megapixel means 10 raised to the power 6. And if you have 10 raised to the power 6 inputs here, then, or the neurons, then the number of weights will just get exploded. Number of weights that your model will is supposed to learn will just explode. I mean, it will take huge amount of time and huge amount of compute. Right? So if you take simple 32 by 32 image, and if it is a color image, you'll have red, green, and blue. You know that, RGB, and you'll have 3 channels. So you'll have 3072 weights. If you have such a small image, then imagine 1 megapixel, 10 raised to the power 6 into 10 raised to the power 6 into 3. This will be the size of your input layer. That would just blow out of proportion. And if you take 200 by 200, it's like that. This is one drawback with respect to your multi-layered perceptron. That is, the number of weights will get exploded. First thing. Second, in MLP, we deal with dense networks, right? Or fully connected network, meaning if you have a network like this, input 4, and if you have a hidden layer, then every neuron will be connected to every other neuron in the forward layer. Every neuron will be connected to every other neuron in the forward layer. That is a disadvantage. Since every neuron will be connected to every other neuron, okay, you are considering each and every pixel value in your image. So if this is your image, and if I'm going to split it into multiple pixels and assume that it is 7 by 7 image, so you'll have 49 pixel values. So you're making use of all those 49 pixel values to get an output. Output could be, is this image a cat, or is this image a dog? Okay, is this a cat image or a dog image? In order to just know that, you're making use of all the pixels. But maybe cat is here. Okay, maybe you have a cat here. Okay, and you have the mustache of a cat here. I mean, the pixels which are surrounding this are really not important for you to make out whether this is cat or a dog. But when it comes to MLP, you're using all the pixels. So you are going with full connectivity of neurons, which is clearly wastage of resources. Okay. And what happens is, if you use each and every pixel to train your model, you're going to overfit. Your model will overfit. Your model will simply overfit. So to counter this, people have come up with, okay, so this is what I was speaking about. You're going to waste the resources. So to counter that, people have come up with something called as convolution neural network. This is the same thing that we have learned, and now trust me, you'll feel as if it's walk in the park, because already we have done this. Computer vision. Say you have an input image, okay, and say you have a filter or a kernel, and you're taking a 3 by 3 filter, and here the size of the image is 5 by 5. You have a 5 by 5 image and a 3 by 3 filter, and the values of filter are given here: 1 0 1 0 1 0 1 0 1. So I'll put that 1 0 1 0 1 0 1 0 1. So you have all those filter values. If you apply this filter on this input image, okay, so let me say filter. Filter is also called as kernel. Kernel is also called as mask. So filter or kernel or mask, you take that, and when you apply on your input image, okay, say you're applying on this patch. Let me take a different color here. So you're applying on this patch. What happens if you apply it on that patch? You multiply 1 with 1, 1 into 1 plus 0 into 1 plus 1 into 1 plus 0 into 0 plus 1 into 1 plus 0 into 1 plus 1 into 0 plus all these. When you multiply and add them, you get 4. Okay, that's the central pixel. You'll get a central pixel that is 4. Now, move this filter one stride at a time. If I say stride equal to 1, then what is going to happen? You are supposed to move this by 1 pixel here. So I'll choose a different color. Move it like this. And then when you move it in this way, you'll get the central pixel. Right? Again, 1 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 0, so on and so forth. When you solve it, you get the central pixel, which is so much. I mean, the central pixel will be 3. Just do it. 1 into 1, sorry, 1 into 1 is 1. 0 into 1 is 0. 1 into 0 is 0. 0 into 1 is 0. 1 into 1 is 1. 0 into 1 is 0. 1 into 0 is 0. 0 into 1 is 0. 1 into 1 is 1. So when you add these, you get 3. Then what you do? You move it again one stride. Okay, you again move it one stride here. Okay, when you move it one stride once again, same thing you do. You take the same filter values. The point that I'm trying to drive here is the pixel values or the filter values will remain the same. They will not change for whatever patch you apply. So if you apply it on this 1 into 1, plus 0 into 0 plus 1 into 0, so on and so forth. When you solve it, you get a value for the central pixel that is 4. Okay, then again move it by stride equal to 1. Stride equal to 1 is the same. So you come down in this way. Okay, by 1. Then what happens? Apply on this patch basically. You take all these values and do a sum product on all these values, and then you get the central pixel value, which happens to be 2. Then move it one stride. Keep doing that. And you get this output image. So when you take an input image and when you apply this filter or a kernel or mask on this input image, you'll get this output image. And here you have these values. All right. Now, how does it appear if I were to draw a simple network? So you have a 5 by 5 image, right? 5 by 5, which is 25. So you'll have 25 neurons here. And you have a kernel which is 3 by 3. So you'll have 9 neurons. When I apply a 9 by 9 filter on this, what happens? Here you'll have 9 neurons. Here you'll have 25 neurons. And it's convolution neural network. It's no longer MLP. From this, we have moved on to this because this has certain disadvantages which we have just discussed in the previous slide. So in the CNN, if you want to calculate this in the output, okay, so if you want to just calculate this, what do? You take all these and apply on the first row, first 3. If you apply on this patch, if you apply on that patch, what happens is you apply in the first row. Okay, so that has 3, 1, 2, 3, and the weights are 1, 0, 1. Then you apply on the second row, second patch. So these two are missed out. So these 2 neurons are missed out. Then you apply here 1, 2, 3, because you have 3 values and 3, 0, 1, 0. And then you apply on the third row. You don't apply on these 2 elements. You apply on the third row, first 3. That is first 3. So these 2 are missed out here. 1, 2, and 3. And here you have 1, 0, 1. 1, 0, 1. Okay, now you have 9 and 25 here, right? This is done on this patch. Now if you move on to say this third patch somewhere here, if you move here, for example, what happens is you take 1, 2, 3 neurons, and then when you do that, or let me do this, it'll be easier for everyone to understand. Let me apply on this final patch. And say you want this final neuron, which is here. So how does it work out? You take the same weights. Weights are the same, they don't change, and apply it on this final patch. That means you go to row 3 and these 3 column values. So you go here somewhere and you apply 1, 2, 3. What will be the weights? 1, 0, 1. Then you go to the next row, these 3, and apply there 1, 2, and 3. And here are the row values 0, 1, 0, 0, 1, 0. And first 2 are left out. And then you go to the next row and then apply it on this. So when you apply 1, 2, and 3, and the weights will be 1, 0, 1. If you observe carefully, the weights that we have here are exactly the same weights that we have here. So the weights are getting shared. And also, you're not looking at each and every pixel value to get the output. You're just looking at the local region here to get this. Okay, so you're looking at the local spatial region to get this. This is the beauty from MLP to CNN. In MLP, multi-layered perceptron, you were using all the pixels and the number of weights were getting exploded. But when you look at CNN, the weights that you have would be the same throughout. If you have 9 weights in the filter, all those 9 weights will remain the same no matter on which patch you apply. So the number of weights that your model has to learn has come down significantly, and thereby your algorithm will be faster. And how are these weights populated here? Automatically they are populated using what? Back propagation algorithm. Same logic applies. There is absolutely no difference. 25 neurons. Okay. Initialize weights randomly. Weights are randomly initialized. Okay, so all these weights are randomly initialized. Then what happens? You calculate the error. Error is nothing but pixel value. For example, your output says that this pixel value should be 4, but maybe actual pixel value is 5. So here you got 5, actually it is, here you got 4, actually it is 5. So that will give you error. So take all those errors, come back and update your weights. One iteration. Okay, for all the images in your data set, pass through your network once and update the weights. It is called as one epoch. So all those things, same things that we discussed in MLP would continue further from here. The only thing is the filter that you apply here, which is this filter, since you're applying on an image, it is called as convolution layer with 2D, because images are two-dimensional in space. Images are 2D, so you call this as 2D convolution filter. And the weights are automatically chosen based on your backpropagation algorithm. Those weights which give you the minimum error would be there in this, and the moment you have that, convolve this on the image to get the output. Okay, so calculate error or cost function. Then third, back propagate to update the weights. This is what we do. Okay, and there are a few more things that we need to discuss, and we are going to discuss about those post our break. So let's take a quick break for 10 minutes and then we'll proceed further. It's 12:35 now. Let us be back by 12:45, and until then it is break time. Size of the filter can be randomly chosen. We will discuss more about that. Yeah, Leelavati. Stride equal to 1 is shifting the filter by 1 pixel on the row and 1 pixel on the right. Okay. So Mr. GT, all the weights are used, right? In MLP all the weights will be different. In convolution it's not the same. In convolution weight sharing happens. In multi-layered perceptron all the weights will be different. Okay, so that's one thing. And convolution also sharing. No, where is convolution share? Yeah, convolution is sharing the weights. MLP doesn't share the weights. Okay, I think we can continue now and discuss further. So here, if you have a 32 by 32 by 3 image, 3 means red, green and blue, and the color channels are called as depth. They're called as depth. And you have a 5 by 5 by 3 filter. 5 by 5 is 25 pixels. By 3 means it's going to cover the depth. Even if you do not mention this 3 here, when you apply a 5 by 5 filter, by default it will consume the entire depth. Okay, it will extend the complete depth by default. Depth is nothing but color. Okay, now when I take that filter and convolve on the image, apply the convolution operation, then you get something called as activation map. Activation map is nothing but the representation or the features that you capture or the features that your model learns. If you use one filter, one 5 by 5 by 3 filter, one activation map is learned. If you apply two filters, two activation maps are learned, so on and so forth. If you apply 6 5 by 5 filters, then you'll get 6 different activation maps. We combine all of these to get a new output, new image. Okay, so you have an image, you can apply as many filters as possible, and whatever filter size you give, it will consume the entire depth. If it's 5 by 5, then it will take 5 by 5 by 3, and you apply 6 such filters, and then you get 6 activation maps. Okay, typically convolution network is a sequence of convolution layers and interspersed with activation functions. You'll have convolution layer, then ReLU activation function, conv ReLU, conv ReLU. In that way, you'll have multiple combinations. Okay, if you're applying if you're applying 6 5 by 5 filters, even if you don't give a depth, that's fine, because whatever is the input image depth, it will consume those many. Input image, if it's a color image, usually the depth is 3. Okay, so if you apply 6 5 by 5 filters, the resultant will have 6 as depth. Then if you apply 10 5 by 5 filters, by default it will take 6 as the depth. Since you're applying 10, the next will have 10. Okay, depth, because you're applying 10. It continues in this way. Next, if you apply 5 5 by 5 filters, then by default it will take 5 by 5 by 10, because the depth is 5. and the output will have depth as 5 because you are using 5 here. Okay, you are using 10, so the depth is 10. You're using 6, so the depth is 6. Input image by default, it has depth of 3. All right. But if you observe here carefully, the size of the image is reducing. When you apply a 5 by 5 filter on a 32 by 32 image, the resultant size has reduced to 28 by 28. And when you apply another 5 by 5 filter on this, the size reduced to 24 by 24. So the size is reducing. By what rate does the size reduce? Okay, so do we have it here? No. Okay, it's there. So I'll move on and then explain that. But even before that, I can quickly take this example wherein we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Say you have a 5 by 5 image, input image. Okay, and say you're applying a 3 by 3 filter on this. When you apply a 3 by 3 filter on this, so this is your input image, and here you have a filter, and then you have an output. What will be the size of output is a question. If you take this and apply it on this patch, okay, you get this central pixel. That will be the first pixel. That will be this pixel. Then you move it by one stride. Then you'll get this central pixel. That will be here. Then what do? You move this pixel one stride once again in this way by one pixel. You'll get this central pixel here. Okay, and then again move it by one pixel here. Then you'll get the central pixel. Then again move it one stride here. Then you get the central pixel. Then again move it by one pixel. You'll again get the central pixel. In this way, you'll get all the pixels, right? But then, why did the size reduce? The size reduced because if I were to get this pixel right here, I need to apply this filter in this way. But then you don't have these pixel values. Hence, you cannot apply this filter on this patch. And hence, you cannot get this. That you cannot get. Right? Hence, the size is reduced. Now, the formula to calculate this output image size is n. If this is n, if the size of the image is n, then you say n minus. If the size of the filter is f, you say minus f. You divide it by stride plus 1. Okay, you're going to divide it by stride and you're going to add 1. So if the stride is 1, this will be 1. So n is 5 here, 5 minus filter size is 3. 3 divided by, we are moving one stride at a time, plus 1, which will be nothing but 5 minus 3 is 2. 2 by 1 is 2. 2 plus 1. So you get 3. And hence the output will be 3 by 3. Okay. Here. This is a typical way your algorithm works. you have an image, you take that image and you pass it through conv pool, conv pool, conv pool, and once you pass through in that way, you get the fully connected network. Okay, finally you get a fully connected network, which has all these various categories. What is this pool? We will learn. But convolution layer, activation layer, convolution layer, activation layer, that is how that's the standard way of representing your data. But if I have a 7 by 7 image, and if I were to apply a 3 by 3 filter with stride equal to 3, then what happens? Yeah, I want to know the answer. Can I apply or not? Okay, let me put a poll question here. And the question is, if we have a 7 by 7 image, 7 by 7 input image, and if you have a 3 by 3 filter, and if you apply stride equal to 3, then what will be the size of output image? Will it be 7 by 7? Will it be 5 by 5? Or will it be a 3 by 3? Or are you going to say that cannot apply? What do you think will be the right answer? Please answer to this. And here is a question. Think logically, take a minute and then answer. Please do not rush in. Give some exercise to your brain. Give some exercise to your brain and please answer. Okay. Okay, so it's a minute now. Let me try now. Here we go. Cannot apply. Majority of y'all are saying it. And that's right, my dear friends. You got it right. So let's see. If you apply a 3 by 3 filter on a 7 by 7 image, and if you want to move it by stride equal to 3, then you skip 3 pixels and apply it here. Okay, wonderful. But then you cannot apply another stride here. Okay. And if I say stride equal to 3, you skip by 3 pixels and come here. Then you skip by 3 pixels and you go there. But then you don't have anything there. You don't have anything here. So it's going to be a very difficult task. Doesn't fit. You cannot apply a 3 by 3 filter on a 7 by 7 input with stride 3. Okay, now let's look at this. If you move it by stride 1, formula would be like this. And if you have a 7 by 7 image, 7 pixels, 7 pixels. And if you have a 3 by 3 filter, then n minus f would be 7 minus 3 divided by stride So it'll be n minus f divided by stride plus 1. It'll have 7 minus 3 divided by 1 plus 1. Stride equal to 1. You'll get 5. So the end result or the output image will be of size 5 by 5. Or it will be n minus f by stride plus 1. If you say stride equal to 2, then it'll be n minus f, which is 7 minus 3 divided by stride is 2. So it'll be 4 by 2, which will be 3. Which will be 2. 2 plus 1, which will be 3 by 3. But the moment you apply stride equal to 3, it'll become 7 minus 3 by 3 plus 1, and you'll get in decimal values. Okay, you will get in decimals. Since you are going to get the result in decimals, you do not, you cannot apply. That is what it means. Okay, then if I were to handle and if I want to ensure that the output image is of the same dimension as that of input image, then you can do, or otherwise also you can do padding, right? So the common way is to do zero padding. If you have a 7 by 7 input image, say 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 7 by 7. Okay, so let me put it this way. You have 7 here and you have 7 here. So it is a 7 by 7 image. If you do a zero padding throughout, then you will be adding 1 pixel here, 1 pixel here. So 2 pixels is what you're adding. All right, so this will become 7 plus 2, which is 9, and or 7 plus 2, which is 9 here. And then if you look at these, you have 7 pixels and you're adding 2 pixels, one here and another here. So this will also become 9. So it becomes a 9 by 9 image. Okay, and what is the formula? If I take this and apply a 3 by 3 filter on that, what will be the size of the output image? That's the question which is being asked. If you do padding by 1 pixel, so n minus f divided by stride plus 1. Okay, so n has become now 9. 9 minus 3, stride is 1 plus 1. So this will be again 6 divided by 1 is 6, 6 plus 1 is 7. So the output image will be of size 7 by 7. Very important thing. Yeah, if you do padding, you can get back the original image. If you want your input image and output image to be of the same size, then how many pixels you have to pad like this? We are doing here 1 pixel, a zero padding with 1 means you are adding 1 pixel throughout the border. Okay, and then the formula is, if you want your output image and input image to be the same, then by what rate should you actually pad it? How many? Here you have done padding with 1, but does it always work? No, it depends on your filter size. Okay, it really depends on what is the filter size here. So if your filter size is 3 by 3 and if your input is 7 by 7. And if you have your filter 3 by 3, then what should be the padding? Padding should be equivalent to 1, so that you get an output which is also 7 by 7. But then if your input is say 7 by 7, and if you're doing 5 by 5 filter, then you won't get, if you do padding 1, you won't get the output as 7 by 7. If you want the output to still be 7 by 7, then the padding would be f minus 1 by 2. Filter size minus 1 by 2. So filter size is 5, right? So it'll be 5 minus 1 by 2, which is nothing but 4 by 2. So you do a padding of 2. Okay. If you have an input image of size 7 by 7, if the filter size is 7 by 7, and if you also want your output to be 7 by 7, then what should be the amount of padding that you do? Okay, when we say padding 2, you add one more layer of pixels around the border. Padding equal to 3 means you take your input image, add 3 layers of pixels around the border. That's padding equal to 3. But how do you know that? This is the formula. If you have a filter size of 7, then the formula is what? It's going to tell that take 7f minus 1 by 2, which will be 6 by 2, which will be 3 by 3. So you do a padding with 3. Okay, only then your output image will be of same size. This is also another thing that you need to know, because when we apply all these things in our Python, in TensorFlow or Keras or PyTorch, you should be aware of all these things. Okay, next. Answer this. If you have an image of size 32 by 32, by 3 means it's just color image. If I'm going to apply 5 by 5 filter size with stride equal to 1 and padding equal to 2, then what will be the output volume size? Yep, please answer. This is an exercise for your brain. Take a pen and a paper and do it. If you understand doing this, you will be able to handle the algorithms very easily. So please do not discount this. Please do it, friends. Take it on a serious note, and then you will learn many things. Yeah, I'm going to give you a quick 2 minutes to solve this. Quick 2 minutes. Okay. Let us see how it goes. Let's see. on who will get it right. Come on, please keep calculating, keep giving me the values. I request everyone to please do it. All right. I think now I need to help you answer this. So here, if you have a 32 by 32 image and if you're padding it by 2, what happens? Let's see first about that. If you have a 32 by 32 image and if you're padding by 2, that means you're adding 2 border pixels throughout. 2 pixels. And you're adding 2 pixels here. So when you add 2 and 2, 2 pixels here and 2 pixels here, total 4 pixels to this. So it becomes 36. Here also it'll become 36. So now the size has become 36 by 36. Okay. And how many filters are you applying? 10 5 by 5 filters. So it's simply put n minus f divided by stride plus 1. N has become 36 minus filter size has become 5 divided by stride equal to 1 plus 1, which is 31 plus 1, 32. So you have a 32 by 32. That is going to be your output image by 10 because you have 10 filters that you're applying. Okay. So next, answer this please. How many weights is your model going to learn? I mean, I'm sure you'll get it right, but then still, please try out. If your input image is of size 32 by 32 by 3, and if you're applying 10 5 by 5 filters with stride 1 and pairing 2, then how many parameters is your model going to learn? Let's see. Who will get it right? Go for it. Answer properly. And you know about this, right? That if you have a 32 by 32 or by 3 or whatever be it, color image, right? And if you're applying 5 by 5 filter, 5 by 5 means 25. You know that the same 5 by 5 filter is going to apply throughout your image. So do you think the number of weights will change? Weight sharing, remember, it will not change. So you'll have 5 by 5 by 3, that's the size. So you'll have 75. Plus if you have bias, it'll be 76. And since you're applying 10 filters, it'll become into 10, which is 760. Okay, this is the algorithm which usually in our advanced modules we walk our participants through that, but it's not needed. So here we have conv relu pool. What is this pooling now layer? This is something that we need to understand. We learned about downsampling, blur the image, downsample, apply Gaussian to blur the image and downsample. This is what we have learned. Okay. And similar to that, you have something called as a pooling layer. The objective of pooling layer is to reduce the size of your image. Right. And then you have this. How is it applied? Let us understand. If you have an image like this, a 4x4 image, and if you're applying a pooling layer of size 2x2, then what happens is you take the 2x2 pooling layer and apply it here. If it is called as a max pool, then what you do is you take the maximum value and that would come in the output. Then you're applying stride equal to 2. So move your image to this stride equal to 2 means by 2 pixel. Since it's max pool, you take the maximum value out of these 4, and if the maximum value is 8, you get it there. Then you apply another 2x2 filter. Okay. Because it is stride 2, you're skipping those 2 and coming here. It's max, so you take the maximum value, which is 3, go for it. Then you apply your 2x2 filter here. Stride 2, so you're moving by 2 pixels. Since it's a max pool, you go with the maximum value, which is 4. There are also other pooling techniques such as average pool. Average pool means take average of all these 4 numbers, and that would be the value that will go here. Then here also take the average of all these 4 numbers. That average will go here. Take the average of all these 4 numbers, and that average will go here. Take average of all these 4 numbers, and that average will go here. If you do an L2 pooling, right? Not many people use this, but if you use, all we do is you take square of each and every number that you have here and proceed further. For example, you do 1 square plus 1 square plus 5 square plus 6 square, whatever you get, you take it there. It's kind of Euclidean, and take a square root of that. Euclidean distance, right? You square it, square, sum them and take a square root, or just add it that way, take it here. It's up to you on what kind of variant you want to use. Okay, that's called as L2 norm. The good part about this is when you apply the pooling, invariance or variance in your data is taken care of. For example, and rotation as well. So you have your images here. A few of the images might be 20 degrees tilted, 30 degrees tilted, 90 degrees tilted, again 20, 40, 90, 60, so on and so forth. So whatever is the rotation here that you see, that rotation will not impact your final output. If you apply pooling, that is called as invariance to local translation. Okay, so you have your conv relu pool. This is a typical sequence in which people use the layers: conv relu pool, convolution layer, activation layer relu, convolution layer, activation layer relu, and then pooling. And then the final result is connected to a fully connected network or a dense network, and then you get an output. Look at what the people who have won the first place on ImageNet competition have done. Alex Krzyzewski, right? What they have done is they have taken an image, they applied 96 convolution layers of size 11 by 11, and they have applied stride equal to 4. They have not done any padding. The next layer that they have used was max pooling layer of size 3 by 3 and stride 2. Then they have applied a batch normalization. Then what did they do? They have applied another convolution layer. 256 is what they've applied this time, of size 5 by 5, stride 1, padding 2. Then they have done a max pool. Then they've done this, then max pool. Then they've connected it to fully connected network. And the final output layer was 100, because this is a 100 class problem. They have used ReLUs, they have used batch norm, they have used data augmentation, they have done dropout, batch size, SGD momentum value, learning rate, decay value, 7 ensemble techniques. Ensemble techniques means you combine multiple algorithms together. So you combine all the 7 CNN models together to get reduced, error or increased accuracy. Yeah, this is what you do basically. So we have learned about a lot of layers, in which we have also learned about Alex Krzyzewski. Because of this guy, convolution neural network has become extremely famous. Look at how complicated this is. If you ask me a question on, hey, how do I decide all these? Experiment. But to experiment, do we need high processing speed? Yes, absolutely. You need to work on graphical processing units. And you guys can practice on Google Colab if you do not have a GPU machine. Free. Up to up to 300 US dollars you can use for free each time. That means it's like if you want to go purchase a laptop, if it's going to cost you say $2,000 for a GPU machine, you need not purchase that, because Google will give you a configuration, a laptop configuration. You go for low configuration, you'll get some laptop, right? But whatever configuration you get for $2,000, similar kind of configuration GPU is giving, Google is giving for only $300. But you need not pay these $300. Up to $300, it is free. But if you want to have even more powerful machine, then you need to pay to Google and upgrade your cloud. And trust me, bring your own cloud is the new way to go. Gone are the days of bring your own device. Okay, so I'm going to stop here. We have done, we have discussed about convolution neural network applications, challenges when we use MLPs, how do parameters explosion happen. Then we started using convolution layers, filters, pooling layers, fully connected layers, right? And we have also looked at AlexNet use case study. And we have done a comprehensive recap on the mind map today. And tomorrow we will just do a quick recap of convolution neural network, and we are going to practically use convolution neural network. Okay, and we are going to practically solve the different use cases pertaining to convolution neural network. Okay, this is what we shall do. Okay, so quickly, once again, I'm going to stop here. Hope you enjoyed. Normalization layer will do normalization or standardization, Ratnakumar. I think you have to watch the initial sessions recorded videos. So once again, let me tell you that there is an attendance form which is given here, and you have a YouTube channel, and get access. You just subscribe, all the videos uploaded will be notified. Okay, here you go. And the initial sessions you have to watch to be able to understand, because a few questions are around basics, right? So you need to have that. It's a number of filter layers, Jose Moses. So I think you guys can go through, watch the recorded videos. Whoever has been attending the session, we have given the LMS access already, and that process is closed for now. You might want to watch the recorded videos and get the maximum out of that. There is striding, which is used usually as an alternative, Jagdish, for pooling layer. Mind map I'm going to post on the WhatsApp group. We will do that. We won't give codes on learning management system. They will not be uploaded because in the recorded videos, already you have entire code which is listed. You have to watch the video and replicate the code. That's the reason. Yeah, assignments are very important. Practice makes you perfect. You'll have access for quite some time. We are thinking about giving for 6 months or so. Yeah, that is also possible, Kishore. You can. Okay. All right, friends. Thank you so much. Okay. And once again, I'm giving you the YouTube link. Please subscribe so that you get access to the future videos. And here is attendance link that you're asking for. We'll also post it on the WhatsApp groups. Thank you and have a great day.